Okay, as you can see, I've got an alkene here, and remember we consider the longest chain. So this is a chain here, and this is also a chain, then this is a chain, but this is a chain of 3 obviously, and this is a chain of 1 2 3 4 5. So it means the longest chain will be this, and 1 is myth, 2 is eth, 3 is prop, 4 boot, 5 is pent, 6 is hex, 7 is pent, and 8 is oct. Yeah, so I've got one branch here, and this branch is a myth. Why? Because there is only one carbon. So if maybe I had another carbon here, then it would be a branch of eth. If maybe I had 3 carbons in the branch, then it would be a branch of prop. So since it's one, it will just be methyl. So we start with the branch, it's methyl. If it was 2, as I said, it was gonna be propyl. So the branch always ends with YL. If it was 2, it was gonna be ethyl. If it's 2, ethyl. 3, propyl. If it was a branch of 4 carbons, it would be butyl. So it means the branch is methyl in this case. And if you can check the number of carbons, 1 2 3 4 5. So we have to number this. Obviously I can't start numbering from 1 to here. I have to start there because it's the one closest to the branch. So that's why I'm gonna say this is carbon number 1 2 3 4 5. So I'm gonna have methyl, and since I've got 5 carbons, it will be methyl pentane. 2 methyl. I have to name the number of the branch. So it's 2 methyl pentane, because this carbon, this branch here is on carbon number 2. If the branch was here, then it would be carbon number 3. So it would be 3 methyl pentane. So let's say, for example, here I had a new example of let's see, I had another branch here. So I have 2 branches now, this branch and this one. So if I had that case, it would be the first carbon is on number 2, the first carbon branch, and the other one is on carbon number 4. So it would be 2 4 to indicate that our methyl branches, because this is a methyl branch and this is also a methyl branch, so it would be 2 4 to show that the first is on 2 and the fourth is on 4, and the second is on 4. So it will be 2 4 dimethyl, because we have 2 methyl branches. 2 4 dimethyl pentane. But what if this branch here was not just it was not American, what's this thing? It was not a methyl. What if this branch here was an ethyl? So we have a branch of 2 carbons here and a branch of 1 carbon here. So in this case, without considering what the longest chain is, obviously in this case the longest chain would be this one. But I'm just telling you now that this is still my longest chain. I'm not changing my longest chain so that you'd be able to understand. So if I had an ethyl here and a methyl here, then I'd number them and name them alphabetically. So this is methyl, which is M. This is ethyl, which is E. So E for ethyl comes before M for methyl. So I'm gonna start with, say, 2 4 ethyl, because this ethyl is on carbon number 4, and then 2 methyl to show that this methyl branch is on carbon number 2, and pentane. Yeah, so that's how we would be able to solve it. Then we also have alkenes. Alkenes are more or less the same as this, but the thing is that here, when we number our carbons, we consider the one that's closest to the double bond. As you can see, when we start here, it means the double bond will start on carbon number 1, 2, 3. So the double bond starts here going that way. But if you start from the left, the double bond will be 1, 2. So it starts on number 2. So we are gonna take 2, which is the shortest, instead of 3. So 1, 2, 3, 4, 5. So it means it's gonna be 1, 2, 3, 4, 5 pent 2 in, to show that it's an alkene. Pent 2 in. Then for the same for alkynes. So when you start from this side, 1, 2, 3, 4. It's triple bonds here. The triple bonds start on carbon number 4 when you start from the left. But when you start from the right, it starts on carbon number 3, because it's 1, 2, 3. So it starts here going that way. So that's why we're gonna take 3 instead of 4. So it's gonna be X 3 ion. So it always ends with ion. So these ones are very simple. Then a haloalkane, you can hear from the explanation haloalkane. So a haloalkane is a mixture of halogens. These are our halogens: iodine, bromine, fluorine, and chlorine, and alkenes. Alkenes, remember, we have alkenes single bonds. So they went to an alkane and they substituted halogens. That's why we have haloalkenes. It's an addition of halogens and alkenes. So as you can see, I've got chloro and bromo, and we are gonna treat them as branches. We are gonna start numbering them and naming them alphabetically. So as you can see, B comes before C. So it means this is gonna be, when I start from this side, it's 1, 2, 3. So my branches will be on carbon number 2 and 3. And if I start from this side, it will still be 2 and 3. So in this case, it doesn't matter. So let's just take 1, 2, 3, 4. Now, I'm gonna say my bromine is on carbon number 2. And I have to start with bromine because, remember, alphabetically, B before C. So it's gonna be 2, 2, to show that there is one bromine on 2 and another one on 2 at the bottom there. So there is 2 bromine. So since there are 2 bromines, it's gonna be dibromine. Dibromo. Then 3 chloro. Then we now have to consider the longest chain, which is butane. Butane. So it's 2 di. If we had, let's say, another bromine here. Let's say we had another bromine here. Then it was gonna be 1, 2, 2. Tribromo. So because it's 3, it's tri. If it was 4, let's say here and here, then we are gonna have 1, 1, 2, 2 tetrabromo, because there would be 4 in that case. Yeah. Then we go to alcohols. The functional group, how we identify alcohol, we identify them through hydroxyl. As you can see, it's OH. So you just name the carbon number. Obviously, this one is one carbon number. When you start from this side, it's 1, 2, 3. And when you start from this side, it's 1, 2, 3. So it's in the middle. So it's gonna be 1, 2, 3, 4, 5. Pent 3 all. If the OH was here, it was going to be on carbon number 2, so it was going to be pent 2 all. So it's always like that: pent 1 all, pent 3 all. If it was here, it would be, if the OH was here, it was going to be pent 1 all. Yeah. And then we have aldehydes, and the functional group is carbonyl. As you can see, carbonyl is C double bond O. So as long as this C double bond O is at the edge, then it's an aldehyde. That's how we identify aldehydes. So when it's like this, it's butanal. If we had 5 carbons, it would be pentanal. If we had only 3, like this, then it would be propanal. So it always ends with nal. If you only had 2, it would be ethanal. So this one is easy. Then it has we call them functional isomers, because as you can see, the only difference between this and this is that this one is in the middle. So we call them functional isomer because when you change your position, then it belongs to a different homologous series. So in this case, it's a ketone. As you can see, the functional group is still the same. But if you can check this, this is a ketone, so it would be 2. This carbonyl is on carbon number 2, so it's 1, 2, 3, 4. So it be but 2, 1 to show that it's a ketone. But 2, 1. If this was, let's say, it can't be at the first, because when it's at the first carbon, it's now an aldehyde, it's no longer a ketone. But even if you had 10 or let's say 7 carbons here, it would be 2 or 7 is hex, so it would be hex 2 or 3 or 4 or 5 1 to show that it's a ketone. So the only difference between this and this is this one wants to know the position. Then the last group, aka carboxylic acids and esters. The same for aldehydes and ketones is applied here for carboxylic acid and esters. So if you can check this one, this C double bond O, then O. Then this also has the same thing here. But the difference between that is that for carboxylic acid, it's at the end, and for this one, it's in the middle of 2 carbons. So that's the difference between carboxylic acid and ester. But otherwise, besides that, they are the same. So this one is at the end, so it's going to be butanoic acid. Butanoic acid. So if it had only 3 carbons, it was going to be propanoic acid. If it only had 2, it was going to be ethanoic acid. So it's always noic acid, hexanoic acid. So you just count the number of carbons. Then when you come here, when you have C and a double bond here, C and a double bond, then from here you go to where your O is. In this case, it's to the left. If you start from this carbonyl here and you go to the left, that's the direction of your branch. Just know that that's the direction of your branch. So which means this is the branch. So our branch is methyl, because that's only 1 carbon. It's methyl. If I had 2 carbons here, it was gonna be ethyl. That's your branch. And then in the main chain we have 3, which is propanoate. So if I had 3 carbons here on this side, it was gonna be propyl propanoate. If I only had 1 carbon here and maybe 5 carbons here, remember this is the main chain, so it was still gonna be methyl, but here it was gonna be pentanoate, because remember we'd have 5 carbons here. Yeah, so that's how it is. That's the difference between carboxylic acid and esters. And we also have isomers. We have different types. We have chain isomers and positional isomers and functional isomers. As you can see, I've got this here. If you can check with functional isomers, I've got an aldehyde here. If you can check this, the name of this will be propanal, because for propanal, the carbonyl is at the end. But once you take it to the middle, it's now a ketone. So it's prop 2, 1. So these two, if you can count the number of hydrogens here and here, they are the same. The number of carbons here and here, they are the same. The number of oxygen here and here are the same. So they are called isomers. So they are functional isomers, if you want to be specific. With chain isomers, this one doesn't have a chain and this one has a chain. So that's why they're called, but they all belong to the same functional group. They are all alkanes. This is an alkane. This is butane. This is butane because there are 4 carbons, but this is, we'll have to consider the longest chain. So it will be 2 methyl propane, 2 methyl propane. But as you can see, they still belong to the same functional group, which is alkanes. And this is our positional isomers. They still belong to the same group, but as you can see, the other OH is at the beginning, which is number 1, and the other one is on number 2. So this one explains themselves. They are positional isomers. The other one is on position 1, the other one on position 2, the other one on position 3. So that's why they are called positional isomers. So we have chain isomers, then positional isomers, and functional isomers.